Good day everyone, my name is Rahinee Nagappan, my metric number is 184929. Today I will present about my final year academic project. My title is on catalytic cracking of fatty acid methyl ester based soybean oil using modified Malaysian dolomite catalyst. So these are my contents for today. There are two types of raw materials mainly used in my project, which is FAME and also dolomite as catalyst. FAME is a type of biodiesel produced from the process called transesterification from vegetables, oils or animals' fat. FAME is actually a renewable oil which can be a substitute to the petroleum diesel fuel. However, the presence of abundance of oxygen in the form of aliphatics and aromatics reduces the quality of the biofuel. Therefore, a method which is a catalytic cracking of FAME using dolomite was introduced. Why do we choose dolomite catalyst as catalyst? Because it is a natural mineral containing compounds mainly like calcium, magnesium, bicarbonates and several other compounds. Besides, it is also a heterogeneous catalyst where it can remove oxygenated compounds while converting them into carbon dioxide, carbon monoxide, methane, hydrogen and also water. So my objectives of my project was to investigate the degradation profile of FAME using TGA in oxygen-free environment with and without catalyst. My second objective was to perform the kinetic study on catalytic cracking of FAME using TGA at various heating rate. And my third objective was to assess the catalytic cracking of FAME at various temperature using lab-scale fractionated cracking system. So why do I conduct this project is because FAME is an organic biodegradable and non-toxic fuel source which reduces the greenhouse gas emission and has lower combustion emission profile on the sulfur oxides. FAME is chosen as our feedstock instead of vegetables oils because vegetables oil contains phospholipids and also free fatty acids, where phospholipids causes catalyst to deactivate and free fatty acids in it causes it to corrode. Production of biodiesel can reduce the dependence on the petroleum crude oil. So these are the materials and equipment used toward my project. So this is the overview of the method of my project. First is to prepare the dolomite catalyst using precipitation method. So TGA was used to analyze the best ratio in FAME for the catalytic cracking. Next is the catalytic cracking of FAME using the best ratio of catalyst. And finally, the product from the catalytic cracking, which is the pyro oil, was sent to the GCMS analysis. This is the schematic diagram of the lab scale fractionated system. So moving on to my results and discussion, my first discussion is about the thermal analysis of FAME. Okay, so there are two types of tests on thermal analysis of FAME, which is with catalyst and also without catalyst. So these are the results of thermal analysis of FAME without catalyst. As you can see, these are the operating conditions used, which is heating rate at 10 degrees Celsius per minute and temperature up to 600 degrees Celsius. As you can see, the temperature degradation without catalyst of FAME was at 291 degrees Celsius. This peak is determined by the highest rate of FAME's oil weight loss. Moving on to the next finding, which is the thermal analysis of FAME with catalyst. In this test, the same operating condition was used except for the ratios of catalyst. Ratios of catalyst used was 1, 3, 5, 7 and also 10%. This TGA was repeated 3 times in order to obtain an accurate and also precise result. So it is concluded that the higher the ratio of the catalyst to FAME oil, the lower the peak temperature degradation. So which explains that addition of catalyst boosts the performance of the FAME oil degradation in TGA by lowering the temperature degradation. So these are the results from the first run, second run and also third run. So as you can see, this is the summarized table from all the 3 runs with different types of ratio of catalyst. As you can see, 10 ratio of catalyst shows the best results because it shows the lowest temperature of all ratio of catalyst shown before this. And it shows the highest temperature difference when compared to the FAME oil without catalyst. Therefore, 10 weight percent was chosen as the best ratio of catalyst. Next, moving on to the next finding, which is kinetics of flame oil degradation. First, we have tested the flame oil using different type of different heating rate with constant catalyst ratio. So 10 weight percent of catalyst ratio was used with different heating rates such as 5, 10, 15 and 20 degrees Celsius per minute. As you can see, higher heating rate, when the heating rate increases, the temperature degradation increases as well, which indicates that shorter reaction time is needed to complete the reaction. So you can see this is the summarized results from the from different heating rates. As you can see, the lowest temperature was at 5 degrees Celsius per minute, which is 262, and the highest temperature was at 301 at 20 degrees Celsius per minute. Therefore, a temperature range for the catalytic cracking to be conducted have been determined, which is from 260 to 301. So with temperature difference of 30, temperatures at 260, 290 and also 320 was selected to conduct the pyrolysis. So moving on to the kinetic analysis of flame with catalyst. So in order to find the kinetic study, which is the activation energy, we need an equation. So a Friedman equation, which is ln beta is the heating rate, dA dt is the conversion rate, A is the Rahinee's equation, Fa is the function of conversion, Ea is the activation energy, R is the gas constant and T is the temperature. So this equation was used to plot a graph of ln heating rate times with conversion rate versus 1 over temperature. Therefore, the slope of the curve is the Ea over R. So we can obtain the Ea from the slope by multiplying with the gas constant. So these are the results obtained at 5, 10, 15 and 20 degrees Celsius per minute heating rate. Therefore, the average heating rate is at 4.50, which shows that lower activation energy requires less energy to crack down the chemicals bond. Therefore, no external or large amount of energy required to initiate this reaction. Okay, next moving on to the crucial part of this experiment, which is the pyrolysis yield. Okay, there are two types of yield produced, which is the liquid yield and also the solid yield. The liquid yield is the oil produced, while the solid yield is the coke produced. As you can see, at 290 degrees Celsius, it shows the highest yield mass produced, which is 6 gram compared to the other two temperatures, and also 141 gram of coke produced, which is higher than 260 but lower than 320. Will be the coke was produced catalytically by the polymerization of large aromatics. Okay, the high 141 gram is considered high, the mass of coke. Okay, this might be due to the high percentage of catalyst loading, which is 15 gram. So since we're using lower operating temperature in catalytic cracking, which is 290, which is considered low, so it might be due to the unreacted flame and catalyst in the flask that contributes to the mass of the coke. Okay, the pyro oil was sent for GCMS analysis, and we have found out that at 290 degrees Celsius, the oxygenated compound produced is at 88.12, which is considered low compared to the other temperatures. Next is the product yield, which is the hydrocarbon yield. At 290 degrees Celsius, we could obtain that it has the highest number of hydrocarbon, which is 11.87 compared to the other temperatures. So the total of hydrocarbon product was contributed by all these hydrocarbons, while this total number of oxygenated product was contributed by all these compounds. Okay, therefore, the optimum temperature of flame and dolomite pyrolysis was obtained, which is at 290 degrees Celsius. Okay, the first reason why do we choose 290 as the optimum temperature was because the yield of the oil was high, which is 6 gram compared to the other temperatures, and also the solid yield was considered low compared to the other temperature, which is 141 gram. Okay, besides, it also produces the lowest percentage of oxygenated compound compared to the other three temperatures, which is 88.12%, and also highest yield of hydrocarbon at 290 degrees Celsius compared to the other temperatures, which is 11.87%. Okay, to conclude, I would say that at 290 degrees Celsius and 10 weight percent of catalyst ratio is the best conditions to conduct the catalytic cracking in order to achieve less oxygenated compound in the film. Therefore, the average activation energy was just 4.50 kilojoule per mole, so there is no external energy needed to initiate the process. So my recommendations are higher temperatures should be tested for the pyrolysis by not just limiting the temperature to 320. Okay, besides, since coke is produced during the pyrolysis, which is the solid yield, the components of the coke should be analyzed as well by sending it to SEM EDX test to know the components in it to avoid the consequences when it's applied to the larger scale. In future study, the pyro oil produced, which is the biodiesel, can be tested on the engine to assess its performance. So that's all from me. Thank you.